Hello guys, welcome to my YouTube channel or David Structural Hub. This is a place where you learn, build and innovate. So today's I want to talk about analysis of statically determinate beam, and under this subtopic I will be analyzing the following types of beams. Number one, single span overhanging beam. Number two, simply supported beams, and number three, cantilever beams. So guys, I'm targeting those students who are pursuing diploma in civil engineering, and we have two programs, that is CDAC level 6 and NEC module 1. And to be specific, I will be handling or solving problems from past papers from CDAC body and the NEC body. So welcome guys. Hello guys, I want to solve a problem from perform structural design and analysis, that is CDAC level 6, July-August 2024. And the question reads, analyze beam in the figure 1 and determine its support reaction. Draw shear force and bending moment diagram. That is 6 marks. So this is the beam you are supposed to analyze and draw shear force and bending moment diagram. So the first thing to do is to extend the line, to extend this line to give you space to draw shear force and bending moment diagram, and make sure the shear force and bending moment diagram is on one page. Extend until to give you enough space to draw the shear force and bending moment diagram. So after doing so, the next thing is to start calculating the reactions at supports. So we have two supports, that is A, which is a hinged support, and B is a roller. So let's begin by calculating the reaction. So this is first thing to note on this beam. It is an overhanging beam and it's a single span overhanging beam. So you will apply the three equations of equilibrium to calculate the reaction at A and at B. So let's begin by summing moments at A equals to 0. So summation of moment at A is equal to 0. You will be calculating reaction at B. So let's see how you will find the reaction at B. So all the forces that will be moving in anti-clockwise direction will be considered as negative, and those forces that will be moving in clockwise direction will be considered as positive. So summation of moment at A. So reaction at B when the reference point is at A. So let's see in which direction is reaction B moving in reference to point A. So it's moving in anti-clockwise direction. So it will be minus 3 times reaction at B. After that, you go to the nearest force to point A, which is a UDL of 30 kilonewton per meter. So in which direction is this UDL moving in reference to point A? So it begins from this and it ends here. So that way. So that is clockwise direction. So it's a plus 30 times. When you are working with a UDL, you first convert to a point load. So it is 30 times the distance covered by that UDL. It is 3. So by doing so, you have converted a UDL into a point load. Then the bending moment for a UDL, it acts at the center of that distance covered by UDL. So it will be the center of 3, that is 3/2. And then we have a 10 kilonewton in each direction. That way. So it's moving in clockwise direction. So it's plus 10 times distance from A, that is 3, plus 2, that is 5. So 10 times 5. Is there any other force? No. So we equate it to 0. Then you simplify by opening the bracket, minus 3RB plus 2 here 1, 2 here 15. So it will be 15 times 9. So it's 15 times 9. You can punch your calculator. 15 times 9. That is 135 plus 135. Then 10 times 5 plus 50 should give you 0. Minus 3RB plus 185 should give you 0. This one, negative 3, when it crosses to the other side, it changes sign from negative to positive. So 3RB should give you 185 over 3/3, which imply RB equals to, you can also punch your calculator. So 185, you divide by 3, it is 61.67. 61.67 kilonewton. Then let's again sum moment at point B. Summation of moment at B equals to 0. So reaction A will be moving in clockwise direction like this. So it will be RA times the distance from where you are summing your moment from, that is point B. So from here to here is 3 times 3. The force which is so close to B is is 10 kilonewton. So in which direction? So that is clockwise direction. So plus 10. The distance from B to 10 kilonewton is 2 times 2. Again, we have a UDL of 30 kilonewton. In which direction? Anti-clockwise. So it will be negative 30 times 3. We are changing a UDL to a point load, and then times a half of 3. We said that a bending moment for UDL, it acts at the center of the beam. As you can see, we have 30 kilonewton meter. The distance is 3. So a half of 3, like that. So no other force. equate to 0. 0. So let's open the bracket. So we have 3 RA plus 20 minus here 1, here 15. So 15 times 9, 135 equals to 0. So plus 20 minus 35, you can punch your calculator. 20 minus 135 is 100. 20 minus 135 is negative 115. So 3RA minus 115 equals to 0. When 100 and negative 115, it crosses to the other side, it changes sign from negative to positive. So 3RA should give you 115 over 3 over 3, which imply RA equals to 38.33. So 38.33 kilonewton. Again, we have the three equations of equilibrium, and number 1 is summation of moments about a point equals to 0. And then number 2, summation of vertical forces should give you 0, and the summation of horizontal forces should give you 0. So for us to confirm if our reaction at A and the reaction at B is correct, so let's use one of the equilibrium equation, which says that summation summation of vertical forces should give you 0, or summation of downward forces should be equal to summation of upward forces. So summation of upward forces should give you, or should be equal to summation of downward forces. So the upward forces are reaction A plus reaction B should give you summation of downward forces. We have 30, which is a UDL converted to a point load. 30 times 3, that is 90. That is 90 plus 10. There is no another force. So RA, we have 38.33 plus RB 61.67 should give you 100 kilonewton. So we have 100 kilonewton should give you 100 kilonewton. So our reaction are very, very correct. Let's draw the shear force diagram. So we'll draw the baseline, and above the baseline is positive, and below the baseline is negative. So let's begin by reaction at A, which is 38.33. 38.33. So you approximate like there, 38.33, and then 38.33, it's a positive. Shear force at B will be 38.33 minus 30 times 3, because it is a UDL and it is acting on the beam downward. So 38.33 minus 30 times 3. So you get negative 51.67. So negative 51 is around somewhere there. So around there. So you will draw a diagonal line. So that you get negative 51.67. After that, we'll take this negative 10.67 plus reaction at B, plus reaction at B. So reaction at B is 61.67 0.67. So you get 10. Again, we'll approximate where 10 is. So somewhere like there. So that is 10. 10 will be constant up to point C. So then at C, it is 10 minus 10. So you'll get 0. This side there is no any other force, so it's just like that. So now we have come up with a shear force diagram. After doing so, you will be required to identify where the shear force is changing sign from negative to positive. Let us call this point Y, because the shear force is changing from this is positive to negative. So this is the point where we will be having our maximum bending moment. So let's say this is point X, and this one will be 3 minus X. So we are supposed to calculate the distance X, because it will help us to calculate the maximum bending moment. So let me create the space. So how will you find distance X? Distance X is calculated using similar triangle rules, whereby X over, this is X from here to here, over 38.33, from here to here should be equal to 3 minus X over, from here to here, 51.67. So you cross multiply 51.67, X should give you 38.33 times 3 minus 38.33X. So which imply X equals to 1.28 meters. 1.28 meters. 1.28 meters. So here is 1.28 meters, and then you take 3 minus 1.28 meters, you will get 1.72 meters. So here we have 1.72 meters. Now, let's now calculate the bending moment. So, bending moment. Bending moment at A is equal to bending moment at C equals to 0 kilonewton meter. Bending moment at Y. Bending moment at Y equals to, the bending moment at this point will be the area of this part. So it will be a half times 38.33 times 1.28. So the answer will be 24.53. 24.53 kilonewton meter. bending moment at B. Bending moment at B will be bending moment at Y, which is 24.53 minus the area of this shaded, from the area of this where my pen is pointing. So it will be a half times 1.72 times 1.67. So here you'll get negative 19 point negative 19 negative 19 point negative 19.91 kilonewton meter. Or the simple ways to do or to calculate the bending moment at B also at B will be minus WL. So we'll have negative 10 times 2 equals to negative 20 kilonewton meter. You can see we have a very small difference between this and this. So that is it. If you want to confirm the bending moment at D is equal to 0, you will say bending moment at D equals to bending moment, bending moment at C. If you want to confirm bending moment at C equal to 0, you will say that bending moment at B plus the area of this shaded part. So it will be 10 times 2. So here we have negative 20 plus 20 equals to 0 kilonewton meter. So having those figures or values for bending moment, we can now draw the bending moment diagram. So you will draw your baseline. So that is your baseline. So this is bending moment diagram. So above the baseline is positive and below is negative. So we have different version of drawing the bending moment diagram. The positive bending moment is considered or is drawn below the baseline, and the next. Now let's now draw the bending moment diagram. So we have said at point A is 0, then at point Y is where we have the maximum, that is 24.53. Let's approximate. So it's 24.53. And then at B, we have negative 20 or negative 19.91. So negative 20 at B, negative 20. So we can join the points. So here we will have a smooth curve. Let me use another pen. So here is a very, very smooth curve. Like that, where we have a UDL, we will be using a smooth curve. Again, another smooth curve up to that point. Then where we have the point load, it will be a straight line. Like that. So here is positive, here is negative. So if you are using strength of material by Komi, you realize that Komi draws a bending moment, a positive bending moment, a positive bending moment diagram above the baseline and a negative below the baseline. But in other books, they draw a positive bending moment below the baseline and a negative bending moment above the baseline. Mostly in civil engineering and structural engineering, they use or they draw a positive bending moment below the baseline and a negative above the baseline. So whichever you use, you are okay. So after doing so, now you can be comfortably uh, pocket your 5 marks out of this question. But I want to add another information, and this one uh, is all about the point of contraflexure. Is it contraflexure or I don't know? Is the point of contraflexure. Point. This is an additional information. So the point of contraflexure or contraflexure is where the bending moment is zero. Is where the bending moment is zero, and it changes the sign from positive to negative. So bending moment is equal to zero at the point of contraflexure. So let's say this point is Z, this one, Z. So at times you may be told to calculate the distance from the left side of the beam to the point of contraflexure, or from the right side of the beam to where the point of contraflexure is. Let let us now calculate the point of contraflexure from the left hand side of the beam. So we'll be calculating this distance. So this is the distance x. So if I can take this part and draw it here, so this is the support, and then up to point Z. So this is point Z, and we have a UDL. Up to this point Z, and we have, let's call this distance C, and we have this distance C. Okay, this is 30 kilonewton per meter. This is RA, and this is Z, the point of contraflexure, where the bending moment is changing sign from positive to negative. So the things here is to calculate this distance C. If we take moment at point Z, so taking moment. So let's sum summation of moment. No, let's calculate moment at z. So moment at z will be this reaction at A in each direction clockwise times c, the distance. Okay? And then we have the 30 kilonewton per meter, which is a UDL. So it starts from this point up to here. So it will be moving in such a direction. So it is negative 30 times c times c. So at the point of contraflexure, moment, you take moment at z. So this one will be RA times c. RA is moving in clockwise direction, then minus. So this is a UDL minus 30 times c distance times where the bending moment is acting on a UDL, that is c over 2. So by doing that, we'll say that RA times c minus 30 c squared over 2 should give you 0. Remember, we have said that the bending moment at the point of contraflexure is 0. So the bending moment at this point is 0. That's why we are equating to 0 to find the value of C. So, but RA is equals to, what is RA? RA is equal to 38.33, is equal to 38.33 kilonewton. So substitute in this equation, uh, substitute where RA is by this figure. So it will be at 8.33 C minus 15 C squared equals to 0. So let's now solve the equation mathematically by saying that, so we have a common C. So let's factorize. So C over that 8.33 minus 15C, close the bracket, should give you 0. So this one implies that either C equals to 0 or that 8.33 minus 15C equals to 0. So we'll solve this one because this one is automatically 0. So 15C should give you that 8.33 over 15 over 15, which imply C equals to, take your calculator, that 8.33, you divide 15, that is 2.56. So 2.56 meters. So the point, the distance is 2.56 meters. So you can say that the point of contraflexure is equals to 2.56 meters from A, and you are done with your solution. So thank you guys, and let's meet in my next session.